computer sits on your desk, in your pocket, and woven into the world around you. So how did we get from counting on fingers to machines that can count the stars? Computer didn't start as something you owned. It started as a job title, someone who computed. This is the story of one idea that kept changing its body, from beads and gears to vacuum tubes to invisible silicon. Same dream, smaller suitcase. That dream is almost poetic. Turn questions into answers, reliably. Not once, but 1,000,000 times, without getting tired or grumpy. Strip away the casing and the hype, and what remains is an obedient engine for method. Give it a process and some material, and it returns a result. Steady, consistent, unsentimental. The first instructions weren't written in code. They lived in patterns, procedures, and the oldest software of all, habits. Long before electricity, humans built thinking aids. The abacus was an early interface, beads you could feel becoming numbers you could trust. As trade grew, so did the need for accuracy at speed. When your livelihood depends on totals, you learn to love a tool that never rounds emotionally. Mathematicians also discovered something profound. A step-by-step method could be described, shared, and repeated. That method is what we now call an algorithm. And once you can describe a method clearly, you can imagine a machine performing it. The dream wasn't a machine that thinks. It was a machine that computes, faithfully, even when the work is dull. Boring, it turns out, is where civilization quietly wins. The future is built by reliable repetition, not dramatic inspiration. In the 1600s, the question became practical. Could we mechanize arithmetic the way we mechanized milling grain? Blaise Pascal built a mechanical adding machine to help with taxes. Many breakthroughs begin with someone sighing, "There must be a better way." Gottfried Leibniz pushed the idea further with machines that could multiply. He also dreamed that reasoning might be handled by symbols, like mathematics. These devices were limited, expensive, and temperamental, but they proved a key truth: calculation could be physical. Then an unexpected cousin of computing appeared: weaving. The Jacquard loom used punched cards to control patterns, instructions stored as wholes. That is a huge moment in disguise. A sequence of holes controlling a machine is programming in a first draft. In the 1800s, Charles Babbage looked at errors in printed tables. He imagined machines that could produce correct results every time. His difference engine aimed to automate specific calculations for navigation and science. But his bigger leap was the analytical engine, a general-purpose computing machine. It would have had memory, a processing unit, and punched card programs. In other words, the modern blueprint, drawn before the modern power outlet. Ada Lovelace saw what that blueprint really meant. The machine could manipulate symbols, not just numbers. Her insight was timeless. The machine follows rules, but humans choose the meaning. If you can represent something as symbols, you can, in principle, compute with it. Babbage's engine was never fully built in his lifetime. Yet the idea survived him, because good ideas don't require immediate hardware to be real. By the late 1800s, governments and businesses faced a new problem: scale. Too many people, too many records, too many numbers for hand methods to keep up. Herman Hollerith used punched cards to process census data faster. Data could now be sorted and counted by machines, information becoming industrial. A punched card is humble, just cardboard and holes. But it introduced a principle that never left us. Information can be stored, copied, and fed to a machine. Over time, punched cards became the language of offices and laboratories. Not glamorous, but steady, like paperwork that decided to become a technology. These systems weren't computers in today's sense, but they built the culture of automation. Measure, encode, process, repeat. Society began to trust machines with truth by procedure, and by the end of this story, you'll see how that trust moved into everyday life. Before computers became physical, they became logical. In the 1800s, mathematicians began treating logic like a kind of algebra. George Boole showed that true-false reasoning could be expressed symbolically. A century later, that would feel less like philosophy and more like circuitry. In the 1930s, Alan Turing described an abstract machine that follows step-by-step rules. Not a product you could buy, an idea that defined what computing could mean. Around the same time, Claude Shannon connected logic to electrical switching. Suddenly, true and false weren't just concepts, they were on-off states. This is one of the quiet miracles of the modern world. We learned to turn thought-like structure into engineering. And once logic could be built, computation could be scaled. The remaining question became brutally simple. How fast can we switch? In the early 20th century, computation met electronics. Vacuum tubes could switch signals quickly, like tiny lamps hired for logic. In the 1940s, large electronic machines proved raw speed was possible. They were massive, hot, and power-hungry. Programming early systems could mean wiring panels and flipping arrays of switches. Imagine updating an app by rearranging the walls of your house. On the Harvard Mark II, engineers found a moth stuck in a relay and taped it into the logbook as a literal bug. Beneath the humor was the lesson. Switch fast enough, and calculation becomes a new kind of force. The next breakthrough wasn't merely faster hardware, it was a new way to organize instructions, so the machine could be reprogrammed with ease. Because speed is impressive, but flexibility is destiny. A fast machine that can't adapt is just a very athletic statue. In 1945, the Edovac Group's ideas spread widely, especially through John von Neumann's draft report. The crucial shift was simple. The how could live beside the what. Instructions stored with data, ready to be rewritten. In June 1948, the Manchester Baby ran its first stored program. A small experimental machine, yes, but it proved the principle on real hardware. In the 1950s, computers moved into universities, labs, and large organizations. Mainframes arrived, room-sized engines serving many users and serious workloads. Early memory lived in drums, delay lines, and tiny ferrite rings, each one a yes or no you could thread into place. Crude, brilliant, and enough to invite bigger questions. Software evolved from panels and patch cords into written languages. Assembly, then higher-level languages like Fortran and COBOL. Less solder, more sentences. Progress often means moving complexity away from humans and into the system. Not because humans are lazy, because humans are needed for the next layer of ideas. In 1947, the transistor was demonstrated at Bell Labs. A smaller, cooler, more reliable switch. Electronics suddenly had a future without fragile glass. Transistors replaced vacuum tubes, cutting size and power demands dramatically. Computers began shrinking from rooms to cabinets, from cabinets to desks. Next came the integrated circuit, packing many components onto one chip. Instead of assembling a city from houses, you could grow the city as one structure. By the 1960s, computers were common in business and science. Still expensive, still specialized, but the direction was unmistakable. Smaller, faster, more accessible. Researchers began linking computers together, and the world subtly changed shape. Networking grew from a practical urge. Let distant machines share work, share messages, and share time. In 1969, ARPANET brought its first sites online. On October 29th, they tried to type log in. The network crashed after LO, and history kept going. In November 1971, the Intel 4004 marked a major shift. A CPU on a single microchip. A whole era compressed into something you could hold. This made personal computers possible, at first for hobbyists, then for households. The Altair 8800 lit a spark, like a campfire for curious minds. Soon came machines designed for ordinary people, Apple II, Commodore, and others. Computing stepped out of labs and into living rooms, cautiously at first. In 1981, IBM's PC helped standardize the ecosystem. And when standards spread, software flourishes, because developers can finally exhale. Interfaces evolved too, from command lines to graphical desktops. The mouse and Windows didn't dumb down computing. They invited more humans into it. Then came VisiCalc in 1979, the spreadsheet that made a microcomputer feel essential, not optional. People didn't just buy a computer and hunt for a purpose, they saw the purpose and went shopping. In March 1989, Tim Berners-Lee proposed what became the World Wide Web. By 1991, the first website was live, and the internet stopped feeling like wires and started feeling like rooms you could enter. Browsers made the web feel navigable, almost friendly. And suddenly, computers weren't only for calculation, they were for curiosity. As laptops improved, computing became portable. Then phones became smartphones, and the computer moved into the palm of your hand. Cloud computing shifted the center of gravity again. Your device became a window, and vast remote machines did the heavy lifting beyond your sight. Graphics processors and specialized chips accelerated new kinds of work. Images, simulations, and machine learning, tasks that thrive on parallel effort. And at the far edge of the field, a stranger kind of machine appears. The quantum computer, not just smaller or faster, built to explore problems in fundamentally different ways. Most of them live in labs, sealed inside cryogenic chandeliers, held near absolute zero. They're not replacing your laptop yet, but they widen the horizon of what computer can mean. Today, computers are everywhere and almost invisible. The most advanced machines often feel like silence until you ask them a question. So how did we get from fingers to phones and all the way to the quantum? By learning to represent the world as information and to process it with reliable rules. The hardware kept shrinking, but the idea kept expanding. Every breakthrough, gears, cards, tubes, transistors, chips, was a new body for the same ambition. And that ambition is not cold, even if the machines are. It's deeply human. To understand more clearly, to build more carefully, to make the future less uncertain. The history of computers is, in the end, the history of questions getting louder. Not because we're lost, but because we finally have tools strong enough to chase better answers. Somewhere, right now, a computer is doing something extraordinary for someone you'll never meet. And almost tenderly, that's what this story has always been about. Guard your curiosity. Aim it carefully. Choose questions that deserve real answers. From counting on fingers to quantum experiments, the same idea kept finding smaller bodies. Big or small, you're always welcome here. At Illumentary,